When designing an FPGA accelerator, a team generally starts with a block diagram. Then they refine it to a clearly defined microarchitectural, wait, we're supposed to do that? Okay, after the step, which we definitely all do, we start coding. You could also take it the HLS route, which ends up resulting in RTL as well. Then we pass it off to the accelerator, which synthesizes it, places and routes it, and then out pops your new accelerator. More to the point, we start with this untimed representation. It's unscheduled, it has no notion of clocks, and then in the microarchitectural phase, we schedule it. We add precise timings to our pipelines. But then we hand it off to the tool, which actually knows about time. We don't know how long signals take to get around the chip until we hit place and route. This design methodology, to me at least, seems pretty bass-ackwards these days. It would have made sense in an era when wire delay was insignificant compared to logic delay. So you could just add up the expected logic delay and get a good estimate of propagation time from register to register. But that hasn't been true on FPGAs for a long time now. Most critical paths you'll find are dominated by wire delay. This is also, by the way, becoming more and more true on ASICs. As the gate delay continues scaling, the wire delay is just stubbornly staying about constant. So today I'm going to be talking about the physical design that high-performance FPGA designs require, and how we're doing it with CIRCT and using high-level models. So Verilog it's just terrible. VHDL is not much better. Basically all RTL level languages are really bad at describing FPGA designs that you really want to be high performance, because, well, I already covered this, wire delay. Say you've got this design, the slide being the physical chip, and this combinational circuit has been extended out to opposite sides of the chip. You insert a register, and you insert another register here. It's only 1 nanosecond because, again, the combinational logic delay is really not that much. So you insert another 2 registers, and then another 2, and 500 megahertz. That's great. But you broke the design functionally because you didn't consider, all the other paths in the design, which relied on that precise timing, the cycle-based timing. And then, this could cascade out to the rest of your design. Once you fix these 2, red paths that were functionally incorrect as a result of your pipelining on the green paths, that could affect everything else. And so it could eventually cascade to your entire design. And don't forget, this is just one critical path. You got to rinse and repeat for all the critical paths and iterate this way. It's generally not as bad as I'm making it out to be, but it is very painful, very tedious, and can often result in what I call off by n cycles bugs. So wire delay has really led us to the necessity of this placement first pipelining, we posit. So this is the idea that if we know where big chunks of relevant logic lives, which is generally application or construct specific, and we assume we know it for this talk, we can estimate the wire delay between these big logic chunks. Now there's a few caveats here to get good estimates. But then if we additionally have a higher level model of that particular construct, we can also preserve the functionality. So the first caveat is that interconnect fabric on FPGAs is not homogeneous like I used to think it was. There are these big discontinuities where you have like dies butting up against each other, so the signal has to go off die. So we need to know about and account for them, and in some cases we can use crossing specific optimizations to help. You also sometimes fight against the RTL compiler. It doesn't know what you're trying to do, so it places registers in absolutely confounding places. So the mitigation here is to place the registers explicitly. So once we have the ability to somewhat accurately estimate wire delay, we can start doing interesting things like optimizing the connectivity of broadcast networks. The one on the left uses point-to-point connections. It's relatively naive. It's likely to get pretty good speed, but it wastes registers and it wastes routing resources. So we can move to a tree-based structure, but if it's not placement sensitive, the speed could be better, it could be worse. The registers, it saves some, definitely, but it could waste routing resources. We could also, if we know the placements, optimize the connectivity based on those placements. So we get, pretty good speed, pretty good, register utilization, and, pretty minimal routing resource usage. So if we're extra lucky and the destinations don't particularly care when they see the data, we can do the systolic thing. Great speed, great register use, great routing resource use. So in terms of optimization, systolic arrays are like a target-rich environment. Once you know that it is a systolic array and you know the structure of it, you have all the constraints, and there's many knobs you can tune. For instance, the placement need not match this kind of rectangular logical structure. It can be a whole mess of different dimensions and all that. Additionally, you don't need to have single cycle connections between things. You can pipeline them almost arbitrarily, at least in a fully buffered systolic array. If it's a more traditional systolic array, then you have some scheduling constraints. But we have this scheduling framework in CIRCT that Julian just talked about to help schedule this. So what is this magical framework that we're building all this on? Well, we're building it all on CIRCT. And in order to understand what CIRCT is, you got to understand what MLIR is. MLIR is a compiler framework that allows for easy creation of dialects in a common format. The general idea being that you design a dialect that's as close as possible to the language layer, and then lower it down through other lower level dialects till you get to your dialect that represents your computational substrate. CIRCT is a set of hardware relevant dialects, a Verilog emitter, a scheduling library, a whole lot of relevant code. And it allows us to create these higher level constructs, such as systolic arrays, broadcasts, and then lower it into these RTL level dialects. It's really great. We designed PyCDE. Basically, I like to describe it as just a really strongly opinionated Python binding to CIRCT. So the primary intent, its only job, is to allow us to easily surface these CIRCT constructs with a not terrible syntax. We're basing all this on low-level CIRCT dialects. So there's already an RTL level dialects in CIRCT that can produce system Verilog. We've recently added the ability to annotate this dialect with placements that get spat out into Tickle placement constraints. Then in the near future, we're going to be creating these mid-level CIRCT operations, broadcast operations, for instance. The FSM and pipeline operations, they already exist in CIRCT, and we'll be looking into ways to physically optimize them. But we're primarily going to start with the systolic array operation. And we'll be using the scheduling framework that Julian just talked about to assist in that work. Longer term, we can start to consider, pulling in and lowering from these higher level dialects, or even a language that you hook up to CIRCT. So, for instance, we're looking into now, the ability to generate a systolic array from the MLIR affine dialect. So in terms of takeaways, deep pipelines are good, The FPGA performance absolutely relies on them. And RTL level is bad since it cannot auto pipeline. We're hoping that the high-level models are going to help a lot with placement and pipelining. And then finally, you should use CIRCT. Thanks.